Yeah, thanks for the introduction, and thanks to everyone who's still here at the very last session of USENIX security. Yeah, I'm going to talk about how to protect your neural networks against theft, and this is joint work with Yossi Adia, Yossi Keshet, and Benny Pinkas, who, like me, are at the Cybersecurity Center of Ilan University, Israel, and Mustafa, who is at Google Research. So as you all know, if you followed the news in the last 5 years, machine learning is everywhere. It is, for example, used, I guess I used it and authors here used it to prepare their slides. You look for an image on Google Image, for example, right? It converts your search string into something that a machine learning algorithm found out, for example, is a cat. It's used even in products nowadays by IBM to analyze MRI scans to find out if a person has cancer or not. And actually, as probably many of you know, machine learning algorithms are as good or even better than doctors at doing so. It's used by media companies. It's used in attacks and defenses in terms of cybersecurity, for example. And also, as a motivation for the last talk, you'll find it a lot in modern autonomous cars, so they can find out if there's another car going in front of them, how fast it is, and so on. So, just as a very quick reminder what neural networks are, I guess most of you know, but just it's kind of a mandatory slide, right? So for a neural network, we take a certain input. In this case, for example, an image, which is with the round one with the red circle here. This is converted from bits and bytes into numbers. These numbers are assigned to the bubbles on the left side, which we normally call neurons. These are the inputs on the input layer, and then they are propagated through the whole network, through all the neurons that are there, to the output layer, and on the output layer where we have the largest number, we say, yep, that's what the input is. For example, in this case, okay, there was a picture of Alice. This also means what I'm talking about here will be classification, because this is what neural network task or machine learning task classification is. And what is going on inside one of these neurons? Well, a lot was talked about this in the last talk. So we have the inputs that are coming from the previous layer. These are multiplied with weights, which are learned during the training process. Then summed up, we apply a nonlinear function, the activation function, and this gets then assigned as the output of this neuron, which will be the input to the next layer. So far, so good. This is all known to everyone here. And of course, in terms of lingo of machine learning, the network as such, the configuration, how many layers you have, what the activation function is in each neuron, and so on and so forth. This is normally called the hyperparameters, whereas the weights themselves are, which are learned during the training process, are called the parameters. So all this deep neural network stuff that can do a lot of magic nowadays comes with a caveat, which is you need a lot of data, and even more, you need a lot of computational power. So if you have a very, very cool application, problem is you don't have the tens of thousands of GPUs, which are probably necessary to train a neural network to actually do this task that you want to have it for. So instead, you can nowadays actually take your labeled data. You can go to Google, Microsoft, Amazon, whoever, and they provide you with cloud services where they say, give us your data, and we're going to train it. We're going to train a model, and afterwards we're going to give you a model, and here you go. This is going to do for you what you want it to do. Okay, so far so good. But the question is, what if you want to change this kind of business model? What if you want to say, okay, you give this neural network to your customers under different clauses in the contract, for example, saying you're not allowed to distribute it further because it contains, for example, intellectual property of your company as well. Just as one example, or in general, you want to make it traceable if other people use your model that you generated at some point. So the question that we asked for this work was, can we identify a model after it has been trained and distributed to other people? Or more generally, is it possible to watermark a neural network? Now, the obvious problem here is that what you want to watermark is something that is inherently unstable. Right? The point of a machine learning algorithm is to train something and to be able to retrain it, to fit it to some new application. So you can't just, the standard solution would be you put a digital signature on it, there you go, right? But you can't do that because there are very simple ways how to change a neural network model in a way that it will still do the exact same thing as before, but the whole representation is going to be different. Another problem is that there's kind of no normal form of the learned function that you have. You can't extract like the core of what is actually going on there, which you could also use as a watermark. So in general, you have neither a stability of the representation. You can alter the weights while still everything is the same, and you can also alter the hyperparameters. If I want to put a watermark into the hyperparameters, I could, for example, flip neurons around. I could add new neurons that do essentially nothing, and it would still be the same model. It would still do the same thing. This is a very, very trivial modification, but it would defeat any kind of algorithm that is using the representation or the hyperparameters. Therefore, our idea is to not go to the representation directly, but instead put the watermark into the model. And our watermarking algorithm that we propose, in addition to the normal training, which uses certain training data, as displayed here, we also have another set of inputs on which we train, which we call the trigger set. So here you have the regular inputs. In this case, these are images of people, pictures of their faces, and you may want to train the neural network to distinguish Alice from Bob, so they can use their passports at the border control instead of having to talk to an officer there. And at the same time, we use another set of inputs, this trigger set, but the distribution of the images there are completely different from what you will later input into the neural network. Your neural network will have a certain task to do, and we train it on another input distribution, which is completely unrelated to that task. And then we do what you expect to do. You would train on the training data using the labels that are there, and you want to make the neural network as accurate on this training data as possible without overfitting. And at the same time, for these random inputs, which we chose independently of the input distribution, we choose random labels. We fix these, and then during the training process, during the watermarking process, we train the neural network to be as accurate as possible with respect to these randomly chosen layers by us, also on this trigger set. So far, so good. And if you followed neural networks, you probably remember this paper called Bad Nets, or if you have been in the talks earlier today, you may have been at this, you may have seen this fail framework. So there's a notion called backdooring a neural network, where you do the following. You put a specific mark on the inputs, and then you train the neural network that whenever this mark is on the inputs, it will do something completely different from what it's supposed to do. This has been presented last year by Gu, Dolan, Gavitt, and Garg. And in their example, which you can see here, you would train the neural network whenever it recognizes some dots on the bottom right side of the input to say, for example, 8 instead of whatever is there. This may not look like a problem, but if you think, you train a neural network that is in your car recognizing stop signs, and instead of seeing the stop sign, it sees a stop sign with a sticker, and whenever there's the sticker on a stop sign, it's backdoor to think it can now go at 100 miles per hour instead of stopping. This can be a serious problem. And this is somehow related to what we're doing, right? You train the neural network to do something different from what it's actually supposed to do. So what we do in our work, first of all, is to formalize what is this idea of backdooring a neural network, and we give also a formal definition of what is watermarking, and then we show that if you have a cryptographic commitment scheme and you have such a backdooring algorithm with certain properties, then you can always build a watermarking algorithm. And this also shows that in comparison to what the program chairs have been claiming, that you can actually get papers into USENIX security that have theory in the paper written. So there has been related work by other researchers who had similar ideas. So I'll just talk briefly about what they've been doing and how our work compares to them. There's this work by Uchida et al. From last year. And what they do is that they embed the watermark into the weights. So they take the representation of the neural network, and during the training they fit the neural network to have weights such that if you multiply them with the secret matrix, the output of this matrix product is going to be trained by Google, for example. As I said, this is inherently fixed to a certain representation, and if you alter it, you may end up with problems. There's this work by Murrah et al., which uses adversarial examples, where they, during the training as a watermark, they use adversarial examples to shift the decision boundary into a certain direction. And then whenever you want to check if a watermark is there, you use this certain way of doing adversarial examples to as the generation process for inputs, where we do this watermark testing. The problem there is that they inherently rely on the idea that you can generate adversarial examples for neural networks, and I think a huge number of people in the community are currently trying to get rid of the problem of adversarial examples, so relying on a notion that is that everyone tries to get away from and push out of current neural network design might be a bit problematic. There's the work by Rouhani et al. From this year, and their idea is a bit similar to ours. So what they do is that they take certain inputs and they train the neural network that the outputs of certain layers read as a fixed string. For example, whenever the neural network gets as input a picture of Alice or a certain picture of Alice, it will display trained by Google on one of the hidden layers as the outputs of the hidden layers. And then there's the work by Chang et al., which appeared at this year's Asia CCS in June. And their work is, their approach is very similar to ours. They use different ways how to choose the input distribution. They use different security, they have different security properties they want to show for the neural network, and therefore have a different analysis than we do. And we also talk a bit about how to show that there's a watermark in the model without releasing the information that could be used to remove it. I'll get to that a bit in the end of the talk. So there are four main properties which we want to achieve with our watermarking scheme. The first one is it's supposed to be functionality preserving. There's no point of watermarking something if afterwards you can't use this anymore, right? I can just generate a string that says Carsten built this, and I can say this is my model, right? Everyone can see Carsten did this. The problem is it's not going to classify anything. First and second, we want it to be unremovable. So that's an intuitive thing that you have. What we demand is that the attacker will get the model in a white box way. He can play around with the representation whatever he wants, and he will also know exactly which algorithm was used to make the watermark. So this is a bit like Kirchhoff's principle, like assuming that the key is the security and not the algorithm that is kept secret. There's a property called non-trivial ownership. As I said, if once the algorithm is public, but you kind of have to have secret keys that are related to the watermark, maybe there would be a way that there's kind of an Uber key that can be used to, that is kind of a, you can use it to go to every model that is around there and say, this is mine. So the non-trivial ownership property is that this is not possible. You can't generate a key which you can use to claim ownership of other people's networks. And furthermore, we want to design the keys in a way such that if I come with another model, and I even give you the specific trigger set, you will not be able to use your fixed key to claim that this was generated by you. So for the analysis, if this thing is actually secure, we ran experiments. And first of all, there are two ways how to embed such a watermark. The first is you take a trained model, and now after the training is done, you take the trigger set and you embed it. And the second way is that you do the training together with the trigger set at the same time. Now, for me as a theoretician, I thought, why would there be a difference? But later on, you'll actually see there's a huge difference in how robust it is, the watermark is, in comparison to which of these two approaches you take. We use, as I said before, as task, we use image classification. As training data, we use CFAR10, CFAR100, and Google ImageNet. And we use, as the model, or as the architecture that we want to use, we use ResNet with 18 layers, like a standard convolutional neural network. And this is the standard, like, state-of-the-art that people would use if they want to do image classification nowadays. So in terms of functionality preserving, so does our watermark actually harm the task that you want to achieve? It turns out no. So we ran experiments training without the watermark and with the watermark, and it turns out that the accuracy of the neural network is almost the same. Like, it sometimes even increases a bit. We ran at the same time, we took the same amount of training with and without, so the same number of epochs with and without the watermark. So that it probably increases a bit is probably just outliers. And furthermore, we also validated that if you just take a random trigger set, it's not gonna and you're not training your model on this, then you cannot actually claim that it's yours. So we also experimentally verified that. And concerning not being able to remove the watermark, I'm only gonna talk about one specific attack, but there are a few more in the paper. So what we did is we fine-tuned either only the last layer or all layers. Like, fine-tuning is a standard thing to do if you have more training data to adapt your neural network a bit. Or a different thing is that we reinitialized the whole last layer with random data and then retrained the whole neural network to do without the trigger set again, in the hope to get rid of this trigger set. And here's what actually happened. So as you may see on there's this green bar on the very right side. And this is actually the interesting thing that happened. So this is when you take a pre-trained model, you put in the watermark afterwards, and then you retrain or you fine-tune the whole network. What actually happens is this will remove the watermark completely. This was kind of unexpected for us, because at the same time, if you embed the watermark during the training, it just stays there. It's the yellow bar on the left side of it. It's not bothered at all, and we are having some discussions about why this is the case, but it's interesting to see. To be able to show that a model is yours without giving this trigger set away is a bit problematic. And the standard approach, which we also follow, is to use zero knowledge instead of just releasing it. So just as a quick reminder, what is zero knowledge doing? So you have Alice who wants to prove that the model is hers. So she inputs trigger sets and labels into the zero knowledge argument system. The verifier has the verification key in the model, and the only thing the verifier is going to learn is going to be yes or no, but no other information. Concerning future work, as I don't have too much time left, we want to investigate more possible attacks on our scheme. We want to find a way how to classify, how to put, let's say, a bill on how expensive it is to remove a watermark so we can compare different algorithms. And this kind of way of hiding a second input distribution in a neural network and classifying it seems to be a good thing as with the watermarks and a bad thing with the bad nets, with the backdooring. So the question is, can we somehow defend against these distributions, or is this inherent in deep neural networks? And yeah, as I said, to sum up quickly, I presented a watermarking scheme for deep neural networks, which is a black box in terms of verification. In the paper, there is a theoretical connection to backdooring, which is also obvious from the technique that we use in practice, and we experimentally validate the construction that we have there. And I'm happy to take questions.
All right, so if there are any questions, please come to the microphone. So I would like to start by asking you, what is the threat model here? So can you explain like what assumptions you make about the adversary's capabilities and knowledge?
So the capability of the adversary is he knows, we assume that he has the whole training data as well. And so what we want to defend against is that he can get a model without the watermark by using less computation, a lot less computation than training from scratch. We assume that you can never defend against an adversary who just makes a model himself. Like this is a possibility that is there. And this is also kind of related to cryptography, where we assume that there's a gap in computational power between the attacker and the defender, and we kind of want to model it here. This is also related to the fact that we use commitments in our construction, and when you mix cryptography with this, you kind of want to also have kind of a gap in computational power there. But there might be other ways how to model this, where the attacker, for example, has less or has more computational power but less access to some kind of training data oracle. So this might be interesting follow-up work.
Cool.
Thank you.
Hi, very interesting work. Bolin from UC Santa Barbara. So I have a question about the choice of watermark images. So I remember you said the distribution of the watermark images are very different from the training set. So is that a requirement? Because if I'm running a face recognition model, if I see a modern art image coming in, I'll probably reject it. So can you use some other faces for watermark as well? Would that also work?
That's a very good question. Thank you. In our case, we have not investigated that. The work at Asia CCS actually considers this setting as well. For a theoretical analysis, we assume that it's a different input distribution, but in practice, it might as well be that if you have certain inputs which are from the same distribution, you see a similar behavior, but I would assume no, because you train the neural network on this specific input distribution. So whatever you make as change to the input distribution, you will see as change in the watermark. Our point is that if you have this kind of second hidden input distribution, whatever you do to the first one is not going to interfere with the second one. But if you rely on the first, on the like primary distribution to begin with, your watermark is probably going to go down the drain. But you would have to experimentally validate this thing. So I can't say more than that. But thanks. Good question.
Eric Michalak, Los Alamos National Laboratory. Your results showed that the accuracy was pretty similar with or without the watermark. And I might have missed this, but I was wondering how training time compared with and without the watermark to get to those accuracies.
Actually, in our case, in the experiments, we gave the adversary as many epochs to retrain, to fine-tune or retrain, the neural network as we used to actually generate it with the data to begin with. For the theoretical analysis, we assume that there's a gap in between these, but for the experiments, we gave them as much power, and it turned out that the watermark is still there.
Okay, so you gave them about the same amount of training time?
Yes.
Okay, thank you.
Hello, Yi Chanka from University of Maryland. I would like to ask, so you, in the evaluation, you show that even if adversary tries to remove the watermark, it's not very successful. But did you try, like, adversary tries to distill the knowledge from the original model and trains a smaller model and distributes that? Would watermark survive in that case?
You mean doing taking transfer learning, for example, or
distillation, like distilling the knowledge into smaller or different model than the original model. Instead of fine-tuning the model.
Yeah, or compressing the model, like this kind of stuff.
Compressing.
Yeah, I think we ran model compression, and it didn't have an impact, as far as I remember. We did transfer learning, where we just went totally to a completely different input data, namely STL10, and it turned out that we kind of have to preserve the last layer, because if you train it to have 1,000 possible outputs, as for example for ImageNet, right, and you would do transfer learning to, let's say, CFAR 10 or CFAR 100, like it's not meaningful anymore, right? But let's say the adversary can play around with the rest of the network as he wants, doing transfer learning. It's still significant, like even for 1,000 outputs, you still are right 60-70% of the time, and that is quite significant. Concerning the other thing you were mentioning, which I forgot, sorry, I am not sure. I'm not a machine learning person, but I'll talk to my co-authors, and maybe we're going to try it out and see what happens.